into our last section here on inequalities in two triangles now. So it's the same concept as our angle-side relationships, right? Kind of the bigger the angle, the bigger the side opposite in a way. But this only works in just one special occasion with two triangles. I can't just apply it to any two triangles. So I like to think of the side angle side inequality. So basically, I'm looking at, I need to have two sides that are congruent to other sides, and the angle in between them, we're going to be able to write an inequality for. Okay, so I need side and a side with congruence, and the angle included or the angle in between we can look at and kind of apply our angle side relationships to that. So if I look at triangle DEF here, I can compare it to triangle ABC. Because if you look closely at the angles that I'm going to compare, I'm comparing 30 to 42. And if you notice, the sides that make that angle are congruent because I have DE congruent to AB. I'm just going to write that here. DE is congruent to AB. And then I have DF congruent to AC. So that allows me to make an inequality concerning my angles with the sides opposite. So I can look at the side opposite. So since I kind of have that side angle side inequality, I can apply this Hinge theorem here and say that EF is less than BC, simply because its angle 30 degrees is smaller than the angle opposite on the other one, which is 42 degrees. So it's the same concept as the angle side relationships, but you have to have that side angle side thought process with the triangles. It couldn't just be two random triangles. You can't just compare the angles and the side opposites on any one. They have to have the side angle side. And we're going to use that. So that's called the Hinge theorem. And if you think about it, it's like a hinge. The hinge is something you can kind of move. So if you have a hinge that's going like this, you should be able to move this top line here. Oh, screw that one up. I could move that angle upwards a little bit, just like a hinge. Okay? So something like that. And we also have the converse of the hinge. The only difference is we're still dealing with the side angle side thought process, except we just have side lengths and we're looking at the angles instead. So if I look at these two triangles, so I'm comparing these two angles right in here, angle D and angle A, and what could I say about those two guys? Well, since I have the side angle side, the sides opposite I can look at, and I should know that angle D is going to be less than angle A because the side opposite 7, right? 7 is less than 9, so I know that angle D is less than angle A. So just like our angle side relationships. Let's use that Hinge theorem here. I'm comparing AD to BD. Well, before I can compare those two side lengths, I got to make sure I have kind of my side angle side inequality thought here. So I got sides congruent to the other side. I'm looking at these two angles, 70 and 68, and then the sides on the other side of that angle. So that works. I can use the side angle side. So I just look at the side opposite the angle. So 70, the side opposite is 80. So I like to just write my 70 here so I can picture it. And 68, the side opposite, is DB or BD, which is 68. Well, I know 70 is bigger than 68, so I know that side length AD is going to be bigger than side length BD by using my Hinge theorem, right? This is by the Hinge theorem. So it's just like our angle side relationships. We call it the Hinge theorem. Okay, and I can also use the converse of the Hinge theorem, right? If I'm given the side lengths instead. I still have a side angle side. If I look, I got side, the angle. So we're looking at comparing this guy to this guy and the side in between. So I just look at the sides opposite. So I know that 5.5 is bigger than 5. So I know that angle ABD, which 5.5 is the side length opposite, I know that that's going to be bigger than angle BDC because the side opposite of that was 5. So you just got to look closely, make sure it's kind of side angle, side thought process. And this one was because of the converse of the Hinge theorem. Converse of the Hinge. Okay, we can also use this to write a range of values for a variable. So if I look at this, it says find the range of values of A. So same thought process, see if it's side angle side, side congruent to side, angle in between, using this angle and this angle, and then the sides congruent to the other side that they share. So I can apply this. Well, if I look, I know that this angle 141, or the angle LDM, I know that it's going to be greater than the other one, angle MDN, because the side opposite 18 is bigger than the side opposite 16. So knowing that, I know that the angle MDN here is going to be less than 141, isn't it? It has to be less than 141 because I know it's smaller than that angle. So let's think about that. So angle MDN is less than 141. Well, I also know that an angle measure can't be less than 0 degrees in a triangle. So I also know that angle MDN is going to be greater than 0 degrees. So it's going to be somewhere in there. I don't know what it is. So what I do is to find my range of values is I set up two inequalities. Well, I know that angle MDN is this over here, 9a plus 15. So I can plug in 9a plus 15 into each of my inequalities. So I'm going to plug it into this first one over here. So I'm going to say 9a plus 15 has to be less than 141 because I know it's smaller than another angle. Then I can do it to this other one as well. 9a plus 15 is greater than 0 because I know it has to be greater than 0. And then I just solve each inequality. So we subtract 15, and I get 9a is greater than negative 15, and divide by 9. And here I get a, I'm going to move this over. I get a is greater than, and I can just simplify that. So negative 5 thirds. And over here I get subtract 15, and we have 9a is less than 126. And then we divide by 9, and a is going to be less than, well, 9 goes in there once, so 3 left over, 36, 4, less than 14. So I can write that as an inequality in the end. So if I look at my two inequalities here, I want to write it as like a range of values. So I always start with my smallest number, which is negative 5 thirds. So I'm going to say negative 5 thirds, while I'm pointing at the negative 5 thirds, is less than a, which is also less than 14. So there's my range of values for a. So basically I just got to think, how can I set up the two inequalities? So here's my given. I can just bring this down. And then start looking at what we know. We know ST is the same as PQ. We know SR is the same as QR. And SP is greater than ST. I'm just going to give it a random value just so I can see this. I'm just going to say something like that. I know those are greater. Just that kind of helps me out. And what am I trying to prove? I'm trying to prove that SRP, so this angle, is bigger than PRQ. So I'm going to say that it's bigger than this angle up here, PRQ. So really, if I can compare the sides opposite, if I can look at the side opposite of SRP and the side opposite of PRQ, if I can compare those, then I'm able to compare the angles, aren't I, by the converse of the hinge? So how can I get SP compared to PQ? Well, I have an inequality with SP, and I know that PQ is equal to ST right here, isn't it? So can't I plug in PQ for ST into here by substitution? Let's go ahead and do that. So SP is greater than PQ. So we substituted that in. Well, now I'm saying that SP right here is greater than PQ. So can't I say the angle opposite is greater than the angle opposite of PQ? Right? It's just that hinge theorem. So I could say that the angle opposite of SP, which we already have up there, is angle SRP, is greater than the angle opposite of PQ, which is PRQ. And this is what I'm trying to prove, isn't it? And that is our Hinge theorem, but it's the converse, right? Because I went from sides looking at the angle, so I just say Hinge theorem converse, or converse of the Hinge theorem, something like that. So converse of Hinge theorem. And I'm done. I'm done. So there you go. Just using that Hinge theorem, kind of the angle side of relationships. Let's try to do the same thing with this guy. So number one, I got RQ is congruent to ST, and I already have that marked in that triangle. That's the given. And I want to get RS, the side length RS, to be bigger than the side length of TQ. So I want RS to be bigger than TQ. Well, I have these angles 1 and 2 in here for a reason. So somehow if I could say that angle 1 is bigger than angle 2, then I could say that RS is bigger than TQ, can't I? Well, how can I get angle 1 to be bigger than angle 2? This goes back a few sections. If I look at angle 1 and compare it to the triangle where angle 2 exists, what do you notice about angle 1? Isn't it an exterior to that triangle? So I know any angle that's exterior to the triangle is greater than each remote interior angle. So I can state that angle 1 is greater than angle 2 because it's an exterior angle, right? So let's say angle 1 is greater than angle 2. And however you want to state this, I could state that angle 1 is exterior to the triangle, so it's greater than both remote interior. Or if I went back and looked at my section, we had a name for it. We just called it the exterior angle inequality. Or I'd be even okay with definition of an exterior angle. And once I get that stated, now I can compare the sides opposite, just like we were talking about. So if I look, angle 1 is bigger than angle 2, so I know the side opposite angle 1 is bigger than the side opposite of angle 2. So I can say that RS is greater than TQ. And now since we applied the angles first, looking at the sides, that's just our Hinge theorem. So there we go, just using the Hinge theorem in the proof with some inequalities. All right, not too many problems for you.